Good morning, ladies and gentlemen. Today, I'm excited to share insight on sustainable practices in hydraulic fracturing, focusing on the innovative use of agro-waste proppants. I am Mansour Zawidawianpour from University Technology Malaysia, and I will be your presenter for this session. We'll kick things off with a brief introduction to hydraulic fracturing, also known as fracking, and its importance in extracting oil and gas from deep underground reservoirs. Then we'll move on to discuss the pivotal role of proppants in hydraulic fracturing operations and issues with conventional proppants. Following that, we'll explore a specialized type of proppant, ultra-lightweight proppant. Next, we'll address the gap in the current industry practices surrounding the adopting of ultra-lightweight proppant. After that, we'll cover the methodology. Then we'll present our preliminary results. Finally, we'll share findings from our experiments. Hydraulic fracturing, commonly known as fracking, is the process of injecting water, sand, and/or chemicals under high pressure into a well to break off underground bedrock to free up oil and gas reserves. This process is intended to create new fractures in the rock as well as increasing the size, extent, and connecting existing fractures in order to extract trapped oil and gas. Hydraulic fracturing is a well stimulation technique used commonly in low permeability rocks like tight sandstone, shale, and some coal beds to increase oil and gas flow to a well from petroleum-bearing rock formation. A similar technique is used to improve the permeability in underground geothermal reservoirs, or EGS. A form of hydraulic fracturing also used in low permeability sediments and other tight subsurface formations to increase the efficiency of soil vapor extraction and other technologies used in the remediating contaminated sites. Once the fracture is created, a slowly composed of fracturing fluid, the proppant is injected to open and maintain a path flow from the fracture to the wellbore. This process results in cracks and breaks that disrupt the underlying layer to allow the transport of hydrocarbon products to the wellbore at a significantly higher rates. Fracturing fluids used to transport proppant inside the fracture include water-based fluids, linear gels, cross-linked gels, oil-based fluids, and foam polyemulsion fluids. Proppant is another main component of the slurry. It is defined as any non-liquid material used to provide structural support for created fracture and to keep it open. Proppants can be sand, nutshells, ceramics, bauxites, glass beads, resin-coated proppants, and combination thereof, which are known as conventional proppants. The global proppant market is expected to reach 12 billion USD by 2026, expanding at a CAGR of around 6.7% during the forecast period 2020-2026. A brief classification of proppant technology, types, performance variables, issues, and qualifications are listed in this figure. As you can see here, production enhancement can be categorized to different disciplines. Hydraulic fracturing is one of them. And then, of course, hydraulic fracturing can be conducted in conventional and both in conventional and unconventional reservoirs. What do we mean by unconventional reservoirs are those subsurface formation that have very low permeability. And then, of course, there are other places in which this technology can be adopted, for example, in enhanced geothermal system and underground injection control. And then proppant, alongside with fracturing fluid and of course candidate selection are the process in which needs to be well designed and selected for hydraulic fracturing. And as you can see, we've classified proppant to conventional and advanced. For the advanced proppant, we have ultra lightweight and we have multifunctions. And for performance variables, we have those proppant that are related to the proppant itself, for example, type, size, shape, and others. Those that are related to the reservoirs, the variables that are involved are closure stress, embedment, prop lengths, which is very important for the design part. And of course, we have operation-related issues, such as well integrity, frac fluids, pumps, and other variables. And of course, there are issues. For example, fine migration is one of the main issues, scaling, proppant flowback, and also screen out and settling. And of course, this settling and fine migration are more related to those proppants and that have high density. And finally, for the qualification parts, we have a stress, strength, thermal stability, chemical resistance, and economics that are involved in selecting the proppants. The essential needs in today's oil and gas industry are saving costs in hydraulic fracturing through improving hydrocarbon recovery, using renewable resources, and pollution preservation. According to the proppant market share by volume, frac sand, resin-coated proppant, and ceramic proppants are accounting for 77.2, 13.4, and 9% of the proppant market, respectively. Remaining 0% of the market comprises of other proppants. Although conventional proppant have extensive application in hydraulic fracturing treatment, some of their drawbacks impose extra costs. For example, frac sand has low crushing strength. Also, permeability of sand is often inadequate. But frac sand is used, fine is produced that will plug the formation and fracture path flow. Also, they can damage downhole and adds extra cost to the treatment. Exposure to silica has created a significant public health threats for hydraulic fracturing workers. Also, the chemicals that is used to cover the proppants in resin-coated proppants also is coated with some polymers that emit hazardous materials and cause severe health damages. Ceramic proppants also have exhibited extreme density. They require a large pumping equipment, viscous fracturing fluids, and high pumping rate to suspend into the fracturing fluid. Higher settling rate of sand, resin-coated proppant, and ceramic proppants have restricted the utilization of slickwater fracturing treatments. In recent years, a new generation of proppant with low specific gravity and settling rate known as ultra-lightweight proppant has been introduced to the proppant market. Utilization of such ultra-lightweight proppant have resulted in reducing settling rate in water, providing improved proppant transport and longer effective frac lengths. Two main types of ultra-lightweight proppant exist, organic-based and inorganic-based. Renewable resource materials such as biomass materials, an example is walnut hull, have shown good potential to be used as substrate for ultra-lightweight proppant. However, their main attractive characteristics is a specific weight and not their strength. Walnut hull will deform easily at higher stresses, and consequently, the conductivity of the pack will greatly decrease. Accordingly, it has been emphasized that strength enhancement in ultra-lightweight proppant is necessary to ensure an improvement of fracture conductivity in hydraulic fracturing. Strength improvement is the key for utilization of renewable resource-based ultra-lightweight proppant. Additional research is of course needed to extend this limitation to the organic-based ultra-lightweight proppants. The current product that developed by my research group can be described as a chemically modified reinforced composite proppant, or CMRCP, an intermediate in cost between sand and resin-coated proppant. The CMRCP is manufactured in multi-stage process. In the first step, raw organic material were crushed and sieved in different sizes. After surface modification, a reinforced natural fiber is formed over the substrate. And then a polymer was used to reinforce the substrate, followed by curing the reinforced layer. An outer coating is formed via thermosetting polymer to manufacture this type of proppant. This slide is for improving the understanding of audience on ultra lightweight proppant, and an example is provided to compare using frac sand and ultra lightweight proppant. Let's first picture of current scenario in hydraulic fracturing, and an example is provided in Barnett Shale. We have two types of wells here, vertical well and then horizontal well. For the vertical well, our production interval is from 100 to 700 feet, and for fracturing we need 750,000 gallons of fracturing fluids and 1 to 1.5 million pounds of 2040S mesh white sand. Normally, rule of thumb is used to calculate the gallons of fracturing fluids. It's 2,000 to 2,400 gallons per foot. Okay, for horizontal well, which which will be increased, the interval which will be increased in folds. We have for horizontal wells, the interval is about 1,000 to 1,500 feet. So what would be the required fracturing fluids and proppants for horizontal wells? So we are considering two cases, and these numbers are extracted from published paper. Okay, so we have sand, which has a specific gravity of 2.85 gram per cubic centimeter and bulk density of 1.62. For ultra lightweight, an example is ULV 1.25. The specific gravity is 1.25, and the bulk density is 0.85. So this is a bulk density which is slightly lower than the sand. So what would be the implication? So in this case, we are using 47% less materials. 50% increase in fracture conductivity is achieved. 74% decrease in fall rate. This is all about the settling velocity, of course. And 35% improved fluid recovery. So in this case, you can see that we have better zonal coverage and longer prop lengths. So the adoption of ultra lightweight proppant presents a game-changing solution in hydraulic fracturing, offering significant improvement in efficiency, productivity, and environmental sustainability. If you remember, we've already classified ultra lightweight proppant to organic-based and inorganic-based. Agro-Waste ultra lightweight proppant are part of organic-based proppants, which are derived from agricultural waste. So two types of these Agro-Waste ultra lightweight proppants are coconut shell and walnut shell. Cellular solids such as these two materials have unique mechanical properties due to their, of course, porous nature. These properties can include compressive strength, stiffness, and energy absorption characteristics. The coconut shell are reported to be composed of 35 weight% of hemicellulose, 15 weight% of cellulose, and 50 weight% of lignin. These materials are suitable for several applications, for example, concrete and using it for safety helmet, offering strength and shock absorbance. The CM RCP is manufactured in multi-step process, and the product illustration are presented in this figure. As you can see, we have a raw coconut shell, and which crushed and sieved in different sizes, hereafter called substrate or uncoated particle. Figure B shows a reinforced natural fiber coat that is formed over the substrate, hereafter called reinforced layer, interlayer, or inner coat. A lignocellulosic material was used to reinforce the substrate. As illustrated in figure C, an outer coating is formed via a thermosetting polymer, okay? So hereafter called final coat. For the methodology, single compression test equipment, universal testing machine, with a capacity for tensile compression, and shear rate was used to characterize the mechanical responses of different coconut shells. And also we've developed a finite element model of an uncoated round particle subject to compressive loading. So this controlled testing approach enabled us to systematically assess and compare the mechanical responses of propant particle, and then to know, of course, the influence of coating on their load-bearing capabilities and behavior under specific loading condition. The finite element model was expanded to encompass all geometries, okay, including the addition of a thin layer, 8 micrometer, to geometries that were originally uncoated. So the chemically modified and reinforced composite propant, CMRCP, featured a reinforced layer measuring approximately 63 micrometer in thickness, followed by a final coating layer of approximately 25 micrometer. Okay, so this figure depicts different geometries with coated and uncoated finite element models. Okay, this slide is for characterization purposes. We have several FSM and SEM images, and we are showing the surface of the substrate, and also we show the non-uniform surface of the substrate. Also, we can see that we have, the substrate is mainly composed of polygons. So after we have the polymer coat, we have a non-uniform layer is composed over the polygons, and here in this picture we can clearly see the rod shape materials, which are our fiber that are covered the substrate of our product. So in this slide, we've compared the experimental and also the finite element analysis for both coated and uncoated materials. So in figure A, both simulations and experimental data show similar strength values for flat coconut shell particles with slightly higher strengths in simulation. Fine particles production begins at 7% plastic strain, indicating material degradation. Coated particles perform better under load due to increase of their surface stiffness from the polymeric coating that is characterized in the previous slide. Plastic strain representing maximum fracture strain is crucial for assessing particle efficiency. It reflects particles' ability to deform before failure, enhancing understanding of propant performance in hydraulic fracturing conditions. Figure B shows comparative strength values for cone-shaped coconut shell particles with higher loads in simulations. Coated particles exhibit better performance with a breaking load of 124.8 Newton. Elastic plastic behavior and surface stiffening effects of the polymeric coating are of course evident. For figure C, round coconut shell particles demonstrate superior performance under load, with a breaking load of 195.6 Newton for coated particles compared to 148.5 Newton for uncoated one. Round particles exhibit enhanced ductility, while flat and cone-shaped particles offer controlled deformation. In this figure, equivalent plastic strain distribution among various particle shapes is depicted, both with and without surface coating. Unaffected regions are in blue, while areas indicating fine particles are shaded in gray post simulations. Consistent 9.60% plasticity is observed across all samples. Remarkably, the round specimen exhibits minimal wear, showcasing its superior performance, whereas the flat samples experience a significant fine generation. With coated surfaces, a distinct behavior emerged regarding fine particles production. Gray region post-testings are concentrated with the coating layer, leaving the core materials elastic, capable of bearing additional loads. This observation aligns with the load displacement curves and the stress contour finding, highlighting the significant impact of coating on propant particle life cycle and durability, vital engineering consideration. This figure illustrates the damage mechanisms and wear production in single spherical particles, comparing those with and without surface coatings. A Python script simulated the wear process, eliminating elements as they reached the fracture strain. Initially, damage occurs in the contact region, followed by gradual degradation of the coating surface, leading to sudden breakage. Uncoated areas reveals voids between layers, indicating failure initiation at the contact points, propagating through voids until complete rupture. This mechanism unfolds in 6 steps over time. Coated particles exhibit material degradation starting at the top side, gradually propagating to remove the coating layer, followed by core material failure. In contrast, uncoated particles show failure initiation on both sides of the contact region, with the bottom side enduring more severe damage. Coated particles demonstrate localized wear, indicating distinctive wear behavior compared to uncoated counterparts. These findings align with literature, suggesting coating enhances stiffness and mitigates wear-induced damage in engineering application. This table provides a quantitative comparison of coated and uncoated coconut shell particles and mechanical performance. Coated round particles shows slightly higher yield load, which is 127 Newton, compares to uncoated ones, 119 Newton. However, coated round particles significantly outperform uncoated ones in braking loads, 203 Newton versus 159 Newton. Coated flat and coated and cone-shaped particles also exhibits improved braking loads. Elongation values remain consistent between coated and uncoated particles. Coated particles consistently absorb more energy during fracture, highlighting the beneficial impact of coating on mechanical properties. This emphasizes the importance of coating for enhancing load-bearing capacity and energy absorption, crucial for material requiring improved durability and resilience. For the conclusion, coconut shell particles explored as ultra-lightweight proppants in hydraulic fracturing. Study emphasizes particle geometry and surface coating effects on mechanical properties. Round-shaped coated coconut shell proppants show significant improvement in stiffness, load-bearing capacity, and durability. Thank you for your attention.